You remember all the chaos around Y2K, right? Everyone thought the world was going to end when the calendar flipped to the year 2000. People were stockpiling water. Banks were freaking out. Your aunt probably had a bunker ready. And then nothing happened. But here's what nobody talks about. We've got another digital doomsday coming. And this one, it's not some maybe it'll happen scenario. It's math. Cold, hard, unavoidable math. January 19th, 2038. Mark it on your calendar, because on that day, at exactly 3:14 a.m., millions of computer systems around the world are going to have a complete meltdown. ATMs will crash. Old servers will fail. Embedded systems in factories, hospitals, transportation networks, they're all going to hit a wall they can't see coming. And the wild part, we've known about this for decades. We've watched the clock tick down. And yet, there are still millions of devices out there that are going to slam face first into what programmers call the year 2038 problem. So what's really going on here? Why are computers so bad at counting time? And more importantly, what happens when they run out of numbers? In the next 15 minutes, you're going to understand exactly why your computer thinks time is going to end in 2038. You're going to see the invisible mathematical prison that old technology is trapped in. And you're going to learn why this problem makes Y2K look like a practice run. Let's start with something you do every single day. You check the time on your phone, you look at when a text message was sent, you see timestamps on emails, social media posts, bank transactions. Every single one of those times, your device is counting. Not with hours and minutes the way you think about time. Computers don't understand 3:30 p.m. on a Tuesday. That's human language. Computers speak in something much simpler. They count seconds. And here's where things get interesting. Back in the early 1970 seconds, when programmers were building the Unix operating system, the granddaddy of modern computing that powers everything from iPhones to Android phones to most of the internet, they needed to figure out how computers should track time. They made a decision. A simple, elegant decision that seemed totally reasonable at the time. They decided that computers would count every single second that passes since one specific moment, midnight on January 1st, 1970. That moment became what programmers call the Unix Epoch, time zero, the Big Bang of computer time. So right now, as you're watching this video, your computer isn't thinking it's Sunday afternoon. It's thinking it's been about 2.1 billion seconds since January 1st, 1970. That number just keeps going up. Every second that passes, every device on Earth running Unix-based systems adds 1 to that count. Your iPhone does it, your Android does it. The servers running Netflix, Google, your bank, they're all just counting seconds since 1970. Pretty simple, right? And it worked beautifully for decades. But here's what those early programmers didn't fully think through. How high can that number go? See, computers don't have unlimited space. They can't count to infinity. They store numbers in little containers called integers. And those containers have limits, hard limits. Mathematical ceilings they absolutely cannot break through. The systems we're talking about, these old 32-bit systems, they use something called a signed 32-bit integer to store time. And this is where the math gets both simple and terrifying. A 32-bit integer means the computer uses 32 ones and zeros, 32 bitses to represent a number. But here's the kicker. One of those bits is reserved to tell the computer whether the number is positive or negative. That's the signed part. So you've really only got 31 bitses to store the actual number. And with 31 bitses, the biggest number you can possibly represent is exactly 2,147,483,647. That's it. That's the ceiling, the maximum, the absolute highest number a 32-bit signed integer can hold. And here's where your stomach should drop a little. Every single second since January 1st, 1970, that counter has been climbing. It's been ticking up, 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 approaching that magic number of 2,147,483,647. Do the math real quick. How many seconds until we hit that limit? Well, 2,147,483,647 seconds from January 1st, 1,970 brings us to exactly 3:14 and 7 seconds a.m. on January 19th, 2038. That's the moment. That's when the clock runs out of numbers. But computers can't just stop counting. Time keeps moving. Seconds keep passing. So what happens when a computer tries to count one more second past 2 billion, 147,483,647? This is where things get properly wild. It's called integer overflow, and it's one of the most destructive things that can happen in computing. Imagine you've got one of those old school car odometers, the ones with physical rolling numbers, and say it only has room for 6 digits. When you hit 999,999 miles and drive one more mile, what happens? It rolls over to 0, it goes back to the beginning because there's nowhere else for the numbers to go. That's exactly what happens with a 32-bit integer when it overflows. When the computer tries to add one more second past 2 billion, 147,483,647, the number doesn't become 2,147,483,648. Instead, it wraps around to the most negative number that integer can hold. And what's the most negative number a 32-bit signed integer can represent? Negative 2,147,483,648. So here's what happens on that morning in 2038. Your 32-bit system is humming along, counting seconds, thinking it's January 19th, 2038. The counter hits 2,147,483,647. One more second ticks by. And suddenly, the computer thinks it's December 13th, 1901. Time doesn't move forward, it jumps backward 137 years in the blink of an eye. Now, you might be thinking, okay, that's weird, but so what? So some computers get the date wrong? Big deal. But here's what makes this actually catastrophic. Modern systems don't just use timestamps to display what day it is, they use time for everything. Think about your banking app. Every transaction has a timestamp. The system checks that timestamp to make sure transactions happen in the correct order. To verify that your paycheck deposited before you paid your bills, to calculate interest based on how long money's been in your account. What happens when the system suddenly thinks it's 1,901? Every transaction you make looks like it's happening 137 years in the past. The banking software doesn't know what to do with that. It's not programmed to handle dates from 1,901, so it crashes. Or worse, it starts corrupting data. Think about security certificates on websites. Those have expiration dates. The system checks the current time against the expiration date. If the certificate's expired, your browser refuses to connect. It's a safety feature. But if the system thinks it's 1,901, every single security certificate looks expired, like expired by more than a century. Your computer refuses to connect to any secure website. Your entire internet stops working. Think about scheduling systems, air traffic control, hospital equipment that schedules medication doses based on timestamps, manufacturing systems that coordinate assembly line timing. All of it relies on time moving forward in a predictable way. All of it assumes that tomorrow's timestamp will be bigger than today's timestamp. And on January 19th, 2038, that assumption shatters. This is what I call the calendar cliff. It's the moment when old systems discover they've been living on borrowed time, literally. And here's what makes this particularly nasty. These aren't just ancient computers sitting in museums. We're talking about embedded systems, devices that were installed decades ago and have been running perfectly ever since. ATMs at your local bank, a lot of them run on 32-bit processors. They were installed in the early 2000s and nobody's touched them since because they work fine, until they don't. Industrial control systems in factories, these things are built to last 30, 40 years. They're controlling machinery, managing production lines, monitoring safety systems, and many of them are tracking time with 32-bit integers. Old servers running critical back-end systems. Companies have applications that have been running since the 1990 seconds. Nobody wants to mess with them because they're too important. They're the systems that process payroll, manage inventory, handle customer databases, your car, if it was made before 2010. Embedded computers in vehicles use timestamps for everything from GPS navigation to emission controls to airbag deployment timing. Medical devices. Pacemakers, insulin pumps, hospital monitoring equipment. Some of these were designed and installed years ago with 32-bit time systems, and they're still keeping people alive today. And here's the sneaky part. A lot of these systems don't display dates to users. They just quietly count seconds in the background. So nobody realizes they're vulnerable until it's too late. You can't just look at a device and know if it's at risk. You have to dig into the actual code, check what processor it's using, verify how it's storing time. But wait, you might be thinking, we've had 64-bit computers for years now. Don't those solve the problem? Yeah, they do. And that's the solution everyone's moving toward. But here's what you need to understand about the difference. A 64-bit signed integer can store numbers up to about 9.2 quintillion. That's 9 with 18 zeros after it. How much time does that buy us? Well, 9.2 quintillion seconds from January 1st, 1970 works out to about 292 billion years. The universe is only 13.8 billion years old. The sun will burn out in about 5 billion years. Earth will be long gone before we run out of 64-bit timestamps. So yeah, 64-bit systems don't have to worry about this problem. They've got time covered for literally longer than the planet will exist. But here's the thing. You can't just flip a switch and upgrade a 32-bit system to 64-bit. It's not like updating your iPhone. The hardware has to support it. The operating system has to be rebuilt. Every piece of software that touches timestamps has to be rewritten. Every database storing time data has to be migrated. For a modern desktop computer, sure, that's doable. But for an ATM bolted into a wall, an industrial robot on a factory floor, a satellite that's been orbiting Earth since 1995, you can't just download an update. And this is where the replacement paradox kicks in. The devices most at risk are the ones that are hardest to upgrade. They're the ones that were built to last forever, installed in places that are difficult to access, running systems that are too critical to risk changing. There's this phenomenon in technology where the more reliable something is, the less likely people are to replace it. That ATM has been working perfectly for 20 years. Why would you rip it out and install a new one just because of some theoretical problem in 2038? Your factory's been running the same control system since 1998. It's never failed, it's never crashed, it's printing money. Who's going to approve the budget to replace something that's not broken? This is what engineers call legacy system inertia. The better a system works, the harder it is to justify upgrading it, until the day it catastrophically fails. And here's what makes the 2038 problem different from Y2K. Back in 1999, everyone was paying attention. The media was covering it. Companies were budgeting for fixes. There was this massive coordinated effort to update systems before the deadline. But with 2038, we're still 14 years out. It feels distant. People assume someone else will handle it. Companies kick the can down the road because they've got more urgent problems today. But here's the thing about deadlines based on math. They don't negotiate. They don't give extensions. January 19th, 2038 at 3:14 and 7 seconds a.m. The math happens whether you're ready or not. Let me tell you about two different organizations. We'll call them Tech Corp and Industry Co. Tech Corp runs a bunch of web servers hosting customer data. They've got some old 32-bit servers still running in their data center. These servers have been rock solid for 15 years. Never crashed. Never lost data. The team knows them inside and out. When someone first mentions the 2038 problem in a meeting, the director waves it off. We'll deal with that when we get closer, he says. It's 14 years away. We've got systems crashing today that need attention. So TechCorp keeps running those 32-bit servers. They figure they'll eventually migrate to new hardware anyway, maybe in 2035 or 2036. They'll do a refresh, plenty of time. But here's what TechCorp doesn't realize. Their customer database is storing timestamps for every transaction. Millions of records, all marked with 32-bit Unix timestamps. When they eventually try to migrate that data to a new system, they're going to have to convert every single timestamp. And if they wait until 2037 to start that process, they're going to discover that some of their application code has been making assumptions about time for 15 years. Assumptions that are baked into how the software works. Fixing it won't be a simple upgrade. It'll require rewriting core parts of their system. Now look at Industry Co. They manufacture medical equipment. Their factory has robotic systems installed in 2005. These systems run on 32-bit processors and use Unix timestamps to coordinate production timing. When Industry Co.'s CTO first hears about the 2038 problem in 2024, she does something different. She immediately orders an audit. Every embedded system in the factory gets checked. Every piece of industrial equipment gets its firmware examined. They discover that about 30% of their systems are vulnerable. Not a majority, but enough to halt production if they fail. So Industry Co. starts a replacement program. They budget for it, they plan it out, they identify which systems are most critical, they line up vendors for new equipment, they schedule installations during planned downtime. It costs money up front, it's not urgent, but they do it anyway. Because Industry Co.'s CTO understands something crucial. She knows that the worst time to discover a problem is when it's actually happening. By 2030, Industry Co. has replaced or upgraded every vulnerable system in their operation. It cost them about $2 million and took 6 years of careful planning. TechCorp, they're still running those old servers, still planning to deal with it later. Notice the difference here? It's not that Industry Co. had more money. It's not that they had smarter engineers. They just understood the nature of the problem differently. TechCorp treated the 2038 problem like it was optional, like it was something that might happen, like they could outsmart it or work around it somehow. Industry Co. treated it like math, like gravity, like something that's definitely going to happen and can't be negotiated with. And that mental shift made all the difference. Here's what most people don't realize about the 2038 problem. It's not actually a technology problem. It's a psychology problem. The technology part is easy. We have 64-bit systems. We know how to fix this. The solution has existed for decades. But the human part, that's where things get messy. See, our brains are really bad at preparing for problems that are far away. We're wired to respond to immediate threats. The tiger in the bushes, the fire in the building, the deadline tomorrow. But a deadline in 2038? That's abstract. That's theoretical. That's somebody else's problem. This is what psychologists call temporal discounting. The further away a problem is, the less real it feels. Even when we know intellectually that it's coming, our emotional brain doesn't treat it as urgent. And for companies, this gets even worse. Most CEOs, most managers, they're not going to be in the same role in 2038. Why spend budget today solving a problem that's going to blow up on someone else's watch? This is the delayed consequence trap. The people who need to allocate resources now won't be the ones dealing with the fallout later. So the incentive structure is completely backwards. And it's not even malicious. It's just how human decision-making works when consequences feel distant. But here's what makes this particularly dangerous. Unlike Y2K, where everything broke on one dramatic day, the 2038 problem might fail gradually. Some systems will hit edge cases early. Database queries that try to schedule something in the future might overflow before 2038. Financial calculations projecting decades out might break first. So we might start seeing weird, unexplainable failures in the 2030 seconds. Little glitches that don't seem connected. Until suddenly, in 2038, everyone realizes these were all symptoms of the same underlying problem. And by then, we're in crisis mode. We're doing emergency patches under pressure, we're making mistakes, we're creating security vulnerabilities in our rush to fix things. This is what happened with Y2K. We got lucky because we had years of coordinated effort beforehand. Billions of dollars, thousands of engineers, all focused on the problem. But we can't assume we'll get that same coordinated response for 2038 because it doesn't feel as scary. It doesn't have the same cultural panic around it, which means the organizations that survive the 2038 transition won't be the ones with the best technology. They'll be the ones who understood the urgency before it was obvious. So here's what's really going on with the 2038 problem. It's not actually about computers running out of numbers. That's just the mechanism. What it's really about is the hidden cost of legacy systems. It's about the fact that we build technology to last, but we don't always build it to adapt. The engineers who designed 32-bit Unix time in 1970, they made a completely reasonable choice with the information they had. They couldn't have known that their code would still be running half a century later. They couldn't have imagined that we'd build civilization-critical infrastructure on top of their timekeeping system. But that's exactly what happened, because good technology sticks around. It gets embedded in other systems, it becomes foundational. And then one day, you wake up and realize that half your world is running on code that someone wrote when Nixon was president. The people who are going to navigate this successfully aren't the ones who panic. They're the ones who understand that every system has limits. Every design choice has consequences that ripple forward through time. They're the ones asking right now, what systems do we depend on? How do they track time? What happens if they fail? What's our migration path? They're not waiting for the problem to feel urgent. They're treating math like it's inevitable. Because here's the thing about integer overflow. It doesn't care about your business priorities. It doesn't care about your budget cycle. It doesn't care whether you're ready. On January 19th, 2038, at 3:14 a.m., every 32-bit system still running is going to try to count one more second. And the math is going to do what math does. The only question is whether you're going to be caught off guard when it happens, or whether you saw it coming and planned accordingly. So yeah, we've got the calendar cliff coming. We've got millions of devices silently counting toward their own destruction. We've got the replacement paradox, making it hard to fix things that aren't currently broken. And we've got human psychology working against long-term planning. But here's what we also have. We have time. 14 years to be exact. That's enough time to audit systems, to budget for replacements, to coordinate migrations, to test thoroughly. To do this right, the organizations that start now won't be rushing in 2037. They'll be watching everyone else panic while their systems hum along just fine. And the wild part? This whole problem teaches us something bigger about how we build technology, about the invisible assumptions we bake into our systems, about how today's clever solution becomes tomorrow's crisis. Every time we write code, we're making choices that ripple into the future. We're setting limits that might seem impossibly far away, but that time eventually catches up to. The 2038 problem is just one example, but it's a perfect example. It shows us what happens when good engineering meets the relentless march of time, when clever design choices hit their mathematical ceilings, when yesterday's infinity becomes today's deadline. So the next time you check the time on your phone, think about what's happening under the hood. That simple timestamp? It's a counter that's been running since 1970. It's been quietly ticking up, second by second, for over 50 years. And in 14 more years, on a Tuesday morning in January, millions of those counters are going to roll over. Some will handle it gracefully because they were upgraded. Others will crash spectacularly because nobody thought to check. The question is, which systems matter to you? Which ones do you depend on? And are they ready for the moment when the math runs out? Because ready or not, January 19th, 2038 is coming. And unlike Y2K, this one's not going to fizzle out. This one's pure math, and math always wins.